Let us discuss this theorem. So in this theorem, we have a scalar field which is differentiable at point A. Then we have to prove that if function is differentiable, then its directional derivative in the direction of any non-zero vector u exists. This thing we have to prove. Let us write the given thing. We have f defines from S to R is differentiable at A belongs to S. Getting? And what we have to prove? Our target is to prove that du f of A. Du f of A means directional derivative of f at A in a direction of u exists for any non-zero vector u belongs to R. Okay, so see, this is a given information. F is differentiable and we have to prove it has directional derivative. See, we will start with epsilon. Let epsilon greater than 0 be given. Let us use the given information. What we have? We have f is differentiable at A. Okay. So you remember the definition of derivative differentiability. So function is differentiable, scalar field is differentiable. That means there exists a linear transformation. So therefore, there exists a linear transformation T from Rn to R. I write here such that so definition says there exists a linear transformation such that for given epsilon greater than 0 there exists delta greater than 0. Getting? But instead of saying given epsilon, we have already considered one epsilon, so I will say for above epsilon, such that for above epsilon greater than 0 there exists delta greater than 0 such that norm h less than delta implies mod f of a plus h minus f of a minus t of h divided by norm h less than epsilon. Statement number 1 I will call it as. Okay, so simply we use the given information. By definition I wrote this thing. Okay, after that I'm going to consider a vector u which is a unit vector. Let u be an unit vector in Rn. Unit vector means what? That is norm of u is equal to 1. Okay, I have considered a unit vector. It means what? Its norm is 1. Let t belongs to R such that mod t less than delta. See what I have considered here? I have considered simply two things. First, I consider a unit vector u. Unit means norm is 1 and t be any real number whose mod is less than delta. Delta we have already got here. Okay. Let us continue, but there is no more space to write. So make a screenshot of it and then we will go further. After that, I am going to consider h. Let h is equal to t. With the help of this unit vector u and this real number t, we have defined this h. H is equal to tu. Let us find norm of h. Then norm of h. But h means what? Tu. Right? See, t is a real number, so it will come outside the norm, but it will have mod. So therefore, mod t norm u. What is value of norm u? It is 1. So therefore, it is simply mod t. But already we have said mod t is less than delta. So this is less than delta. Get it? So we have got norm h is less than delta. When norm h is less than delta, then we can use statement number 1. So therefore, from 1, what can I write? Statement 1 says mod f of a plus h minus f of a minus t of h divided by norm h less than epsilon. By statement number 1, I can write this thing. Let us put value of h here. What is value of h? Therefore, I will write mod f of a plus h means tu, right? Minus f of a minus t, h means tu, correct? Divided by norm tu less than epsilon. So this part is not required. Let me remove it and then we'll go further. It is not required. So let us use this space to solve the remaining part of this problem. Okay. See, therefore, mod f of a plus tu minus f of a. See, t is a linear transformation, and when you consider a linear transformation, if there is any constant inside it, you can take it outside. So similarly, t is a constant which is a real number, so it will come outside t. So therefore, minus t of u divided by, see here also t is a real number, so it can come outside the norm. So therefore, mod t norm u less than epsilon. So therefore, I can write mod f of a plus tu minus f of a minus t of u divided by, see norm u is 1 since u is a unit vector. So therefore, mod t less than epsilon. See, numerator has mod, denominator also has mod. So you can take a common mod here. So therefore, I can take a common mod. Get it? So the numerator divided by t only. But I can divide separately. That means, see, what can I write? F of a plus tu minus f of a divided by t. If I divide it by t, t will get cancelled. So minus tu less than epsilon. So this is less than epsilon. So that means, so therefore, limit, in terms of limit, I can say limit t tends to 0, f of a plus tu minus f of a divided by t is equal to t of u. Have you seen it anywhere? This is nothing but definition of directional derivative. So therefore, directional derivative of f at a in the direction of u is equal to t of u for all unit vectors. Okay, this is for u is unit vector, no? So all unit vectors u in Rn. So this is true for unit vectors only. I will call it as equation number 2. A very important thing we have proved here. But see, we have to prove our result for any arbitrary vector, non-zero, any arbitrary vector. We have proved right now only for unit vector. So let us discuss it now for any arbitrary vector. You can make a screenshot of it, then we will go further. So now let us consider any arbitrary vector, since finally we have to prove our result for any arbitrary vector. So let W be any non-zero vector of Rn. Let W belongs to Rn be any non-zero vector. See, if you have any non-zero vector, okay, we can find corresponding unit vector by dividing it by its norm. Okay, so therefore, u is equal to W upon norm W is a unit vector. Is an unit vector. Okay, so it is an unit vector. If you divide any vector by its norm, 100% we will have unit vector. Okay, so therefore u is a unit vector here. If I shift norm W, so therefore W is equal to u norm W. A very important thing we have got. I will make box to it. Okay, so now consider directional derivative of f in a direction of W at a is equal to, definition says, limit t tends to 0 f of a plus tw minus f of a divided by t. By definition we can write. So this is equal to, what will I do? Limit t tends to 0 f of a plus, W means what? W means u norm W. So therefore t norm W u minus f of a divided by t. We have some space here, so let us utilize it. This is equal to limit t tends to 0, okay, I will copy the same here, what I'm going to do, see, f of a plus t norm w u minus f of a divided by t. Same thing I wrote, getting same thing I wrote. So what will I do? I will simply multiply and divide by norm w. Okay, so at numerator in bracket we have t norm w, in denominator also we have t norm w. I will call it as t dash. So therefore limit, I am calling it as t dash. So t dash tends to 0 now. F of a plus t dash u minus f of a upon t dash into norm w. So I will mention where t dash is equal to t norm w. See, doesn't matter, both of them are real numbers, so product of two real numbers is again a real number. This is equal to, see here, this is definition of directional derivative, right? This is definition of directional derivative. T is there, t dash is there, or whatever is there, doesn't matter, getting? So see, if the for actually this is definition of directional derivative. So directional derivative of f at point A in a direction of u, this thing we have got, into norm w. Okay, now from equation number 2, what we have? Du f of a is nothing but tu, getting? So this is equal to tu into norm w. Okay, let me remove this part, it is not required. I should mention from equation number 2. Let me write that thing. From 2. Okay. See, this is a constant. Norm w is a constant. T is a linear transformation. So if you have any constant, in case of linear transformation, you can take inside, you can take outside, doesn't matter. So I can do the same. So this is equal to, so sorry, this is u, tu. So yeah, what can we write? This is t norm w u. We have seen it somewhere, norm w into u. Yeah, it is, norm w into u is nothing but w. So this is equal to t of w. We are getting, t means what? Linear transformation, which is nothing but total derivative. So the total derivative we can write in this way also. df of a of w. Getting? So actually we have started with this one, dwf of a, and finally we got df of a w. That means this is actually a required thing. See, let me complete this proof, just make a screenshot of it, then we will go further. So in this way we have proved it for unit vector, for non-unit vector. So therefore we can conclude, yes, so directional derivative df of a exists, and which is equal to total derivative of f at a, getting, which is operated on u. So this is a required proof. Make a screenshot of it, after that we will stop. Thank you, bye bye.